Greetings, students. Today we are going to discuss the Hartree-Fock method, which was the first attempt to try to solve for the energies and orbitals of many electron atoms. This is a computational method. We'll get into the computational details a little bit, but we'll save computational chemistry and the major discussion of that for the future. The goals for today are going to be to describe the Hartree-Fock method for calculating the orbital energies, to explain, the general technique, how it works and how it gets the energy. Then we're going to look at the Aufbau Principle, which is one of our principles for arranging electrons and atoms that we have from Gen Chem. And you will know this as you put electrons in the lowest energy orbitals first. And we're going to briefly at the end look at how we can explain periodic trends using the predicted orbital energies. So last class, we had difficulties when we encountered the Schrödinger equation for many electron atoms. The main problem is that when you have three or more masses that are moving and influencing each other, we cannot analytically solve the Schrödinger equation. So what this means for us is that we cannot actually solve for the eigenfunctions, which are the orbitals, or the eigenvalues, which are the energies of many electron atoms. In Gen Chem, you learned all about orbitals for every atom, so there must be some way around this conundrum. Today, we will go over the first attempts to solve the Schrödinger equation for these many electron atoms, and we're going to talk, like I said earlier, about more advanced computational techniques later. The first attempt to solve the many electron Schrödinger equation is known as the Hartree-Fock self-consistent field method, combined with the variation method. So we'll start by talking about the variation method, as you can see in the slide here, and then we'll go into what this Hartree-Fock self-consistent field stuff is. With the variation method, we are using a way to solve for the eigenfunctions and eigenvalues of the total energy operator. So we know that our energy value, right, our E naught, is the expectation value. So we could operate on some wave function psi naught, the ground state, use the total energy operator, multiply by the complex conjugate of that. And then if the wave function is not normalized, we have to integrate with the square of the magnitude of the wave function. If the wave function is normalized, that would just be a 1 in the denominator. And this is how we can get our energy, assuming that we're using the ground state eigenfunction psi naught. The problem is we don't know what psi naught is, so we can't get an energy value, right? So we have an equation with two unknowns, and then how do we solve it? What we are going to do is we're going to make a guess. We're going to have What we're going to do is we're going to make a guess. We're going to come up with a wave function that has to follow all of our quantum mechanical postulates and try to guess a good function and then see what energy that gets us. And one of the ways that quantum mechanical calculations have been improved over the decades is improving the guess. The better the guess is, the more accurate the energy that we predict is going to be. So what we need to do is use the variation theorem, which states that if we have a guess, so here our capital phi is our trial wave function. If we make up some wave function and evaluate it according to the expression that would give us our actual energy if we use the actual wave function, we will always get a value that is greater than, or in the case that we use the exact function, equal to, so in general, greater than the actual energy. So in the homework assignment for today, you're going to apply the variation method for a trial wave function for the particle in the box, and you can compare that to the actual energy. And you can follow along with page 490 and 491 of the textbook, which will go through this problem. And we'll see some of that. I'll go through the conclusions in the slides here, and you're going to go through the actual math in the homework. So what we can see here is we can come up with a trial wave function as follows. So this is for the particle in the box. This, of course, is not a sine function, right? We know that the particle in the box solution should be sine n pi x over a, and what the heck is this? Well, it turns out that this is actually a valid wave function for the particle in a box, right? What did we need? We needed a wave function that was 0 at x equals 0 and 0 at x equals a. You plug in 0 and a into this function, and you'll see that every term has an x. So when you plug in 0, they're all 0. And when you plug in a, every term will cancel out. So here we have a over a is 1 minus a cubed over a cubed is 1. So that term goes away. And this term will also cancel out. You end up with 1 minus 1/2 times 2, which is equal to 0. So this wave function satisfies our constraints for the particle in the box. So it is a potential wave function. And you can see that here. So the sine curve is shown in red, and our crazy polynomial function is shown in purple. And you can see that it actually kind of looks okay, right? It looks like a sine curve. Of course, compared to the actual sine curve, it's not great. And so the way that this problem will go and go about this is to first assume that alpha here is equal to 0, solve for the energy, and you get an energy of 0.133 h squared over ma squared. Now, the energy should be h squared over 8 ma squared, which is 0.125 h squared over ma squared. So we can see their variation theorem is true. We are greater than our energy. The next part of the problem is going to be to go through and do a little bit of this work here. We can evaluate what this alpha should be to get the best fit. And so essentially you plug in alpha, and then you try to maximize alpha, which is what this is here. We evaluate this expression and set the derivative equal to 0. Where do we get what is alpha? And we come up with a value for alpha that gives us an energy of 0.127 h squared over 8 ma squared. So much closer than this. And we can see that this is a kind of bare bones way of how this technique is going to work. It's going to predict an energy that's going to be greater than the actual energy. And you can see as we do this, we get a better wave function that better approximates the actual wave function. So how do we apply this variation theorem to the orbitals for many electron atoms? We start by looking at the approximations that we discussed last time. So namely, this is going to be the orbital approximation and the effective nuclear charge approximation that ignores electron correlation. So we have some kinetic energy part of our wave function, some effective part, and the V effective part is taking into account the effective nuclear charge approximation. So it's ignoring the electron correlation. So this model is only as good as those assumptions allow it to be. And we can solve this and get energy levels for all of the orbitals that are solutions to this equation. Since in this case, we have ignored the electron correlation, all of the orbitals are going to have the same shape as they would in the hydrogen atom. So that means that the angle component is still our spherical harmonic functions. And what's going to be different is the radial portion. And that's because our electrons are now feeling a different effective nuclear charge based on the orbital, right? We have a different effective nuclear charge for the 1s or the 2s or the 2p orbital. And this is different, of course, if you have a helium or a lithium or any other kind of atom. Now, we still have the problem, though, is we don't know what these functions should be. We don't know what our radial functions should look like. And so we have to come, just like we saw for the particle in the box model a couple slides ago, we have to come up with a good guess. So what is the guess for our wave function? And what actually happens is that our guess is actually multiple functions, and we'll see why that is here in a second. So a naive guess would be to use STOs, which stands for Slater type orbitals. And these orbitals are used historically, and they have the same functional form as our solution. So here you can see our function would have r e to the minus zeta r over a naught. And this is exactly what our 1s orbital solutions look like for the hydrogen atom. And you can do this, and this works. You can get Slater type orbitals for s and p orbitals and so forth, and you can get some answer. However, we don't need to use Slater type orbitals. We can use any well-behaved function as a good guess. Like we saw on the last slide, we could use a polynomial instead of a sine curve. And what we do, and you might be able to guess this from the name of the program that does quantum mechanical calculations, is we use Gaussian functions. And we use Gaussian functions because they are easier for computers to handle. They're easier to take derivatives of and integrate and so forth. Now, that's well and good, but you might be looking at these and thinking a Gaussian function is a garbage approximation for the hydrogen atom. And of course, that's true. So here we see the Slater type orbital for the hydrogen atom, and here we see a Gaussian function that's trying to best approximate that Slater type orbital, and it's totally garbage. It's nowhere near the peak. It's much more rounded. It kind of gets off here in these outside regions and so forth. So how can we use Gaussian functions? And this is where this sum comes in. So it turns out that the sum of Gaussian functions can actually approximate a Slater type orbital pretty well. And this goes all the way back to what we talked about before, using our eigenfunctions to approximate any other function. We can add a good number of Gaussian functions together and become closer to our Slater type orbital, our exponential decay. And so here in this picture on the right, what we can see is that if we add 3 different Gaussian functions together, we get a shape that's pretty good compared to our hydrogen atom 1s orbital. And the more functions we use, the better we would get. So now that we have a basis set using some number of Gaussian functions, how do we actually calculate the energy? So we talked about the variation method, but we have a problem here. We can't quite use the variation method as it's written. To solve for the energy of a single electron, right, for electron 1 in this case, we need to know the effective potential of electron 1, which depends on all the other orbitals. So we don't know the function, and how can we guess, right? How can we get a potential if we don't know what the orbitals look like? We're trying to get the orbitals, and to get the orbitals, we need to know what the potential is, and to get the potential, we need to know what all the other orbitals look like, and so forth. So how do we go about doing this? So the computer will use an iterative approach to solve for the wave functions. So what the computer does is it guesses a trial wave function, this phi j here, and it uses that trial wave function to calculate an electron density and predict a V effective. It uses that V effective then to modify the trial wave function, because now we have the effective potential from all the other orbitals. We can build that back in, and we get a new wave function. We use that to get a new V effective, and then a new wave function, and so on, until we get what's called a self-consistent model, where iterations no longer change the energy. So we reach an energy minimum, and we say, well, at this point, this is the best energy that we can get. We've actually achieved the minimum here. And so we can look and see, and of course, what we would find is that the more basis functions we use, the larger, the better the energy would get, the closer the energy would be to the ideal energy. However, what we can see is that in practice, we don't really need to do too many. So for helium, one function gets an energy of negative 77.48, 2 functions get negative 77.87, and then 5 functions gets a little bit greater, a little bit more accurate, but not very much. And so we can see we don't really get much more accurate by using 5 functions, and it takes a whole lot more time than by using 2 functions. Our difference is 0.0001 or 0.0002 electron volts. Another thing that you're familiar with is this zeta as the effective nuclear charge. And this is only true if we use a basis set of one function. So here we can see when we use one function, we get a zeta of 1.6875. And this is actually the effective nuclear charge that we have for the electrons in the 2s or the 1s orbital, the 2 electrons in the 1s orbital for helium. Now, when we have higher functions, our zetas don't really make sense based on effective nuclear charge. For example, we have a zeta of 2.9, and that makes no sense if the greatest nuclear charge we could ever feel is 2. So the effective nuclear charge approximation comes from using basis sets of only one function. We can also see the consequences of ignoring the electron correlation in this table. So naively, what we would expect is that the total energy for the helium atom is equal to the sum of the 1s orbital, right? We have an energy for one electron, and they're both in the 1s orbital. So if we add those two together, we should get the total energy. However, we can see that that is not the case. So here, the total energy is negative 77.8, when the 1s orbital energy is about -25. So if we doubled -25, we get -50, and we're way off. Now, why are we way off? Well, we're ignoring the electron correlation, which doesn't mean we're not accounting for it. It means we're actually double counting for it. So we're treating electron 1 as if electron 2 is spread out over the nucleus and repels it in some way, which increases the energy and makes it less negative for the 1s orbital energy. But we also do the same thing for electron 2. So we count that electron-electron repulsion in both terms here, which gives us a less negative or a smaller number, so that when we add them back together, we've double counted the correlation to the tune of 27 electron volts, which is a pretty big deal compared to a total 77 electron volts. We can compare this to experimental data. So the double ionization energy of helium is 79 electron volts. So it takes 79 an electron volts worth of energy to remove 2 electrons from helium, and we're predicting -77.9 energy. So we're off by 1.1 electron volts. And again, that comes in from these approximations that we have used. If we don't use these approximations, we can get more accurate predictions. Here we can look at some of the effective nuclear charge, and you can see again for helium, the effective nuclear charge is exactly what we get from this single zeta basis set. And these other effective nuclear charges are different based on the different predictions that are used, based on the different orbitals that are applied. We can look at some calculated orbitals and they show that they do the same kind of thing that we expect. So on average, electrons in higher subshells are further away from the nucleus. So in the blue line here for neon, we see n equals 1, and the red line we see n equals 2. And the same thing in argon, we see 1, 2, and then 3, and then krypton we can see here is further out. And so our predictions are what we expect based on our models. Another thing we can do is compare these two experimental results. So we saw that the double ionization energy for helium looked pretty good. What about these other atoms? What we could compare is either to something like ionization energy or electron affinity. It turns out that the electron affinity is not as straightforward, but the ionization energy is pretty good as a tool that we can compare. So when we compare experimental ionization energy to the Hartree-Fock energy, we get a pretty good linear line here. So we're getting almost a 1-to-1 correlation. Again, deviations from this prediction are due to the approximations that we're making here. Another thing we can do is look at the energy levels of the orbitals. So here is a chart of the energy level of the orbitals, and we can see that basically they go down uniformly. So if we look at the 1s orbital, starting with helium and going down, the energy gets lower and lower and lower and lower because, of course, the nucleus gets more positive. The electrons are being held tighter in the 1s orbital to the nucleus, and we see that same general trend. We also see what we expect based on our Gen Chem understanding. So if we look at 3 here, we see that the 3s electrons are lower in energy than 3p electrons, for lower in energy than 3d electrons. So that is something that we expect based on our understanding from Gen Chem. Here we have the quantum number L also playing a role in energy. So if we look at the orbitals, what we note is that the 3s orbital, and I mentioned this before, has a little bit of density all the way out here close to the nucleus, which means that it's going to feel a higher effective nuclear charge, which is going to lower the energy for the electron in the 3s orbital compared to 3p, and then 3p compared to 3d. So we see this hierarchy in terms of energy. Now, what we don't see is something that we were taught in Gen Chem. And we were taught in Gen Chem that electrons filled in orbitals in this way, that the 1s was lowest in energy, followed by 2s, followed by 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, in this way, right? And we were taught this, and we said, well, this is lower in energy. We were taught that the 3d, the 4s electrons were lower in energy than the 3d electrons, so they fill first. But let's look at this data. Right? The lowest energy is the 1s, then 2s, 2p, 3s, 3p, 3d. Right? The 3d electrons here are always lower in energy than the 4s electrons. So why do we say that the 4s electrons are filling first? Well, in chemistry, if something is happening, right, what happens is always the lowest energy. That's, that goes back to, physics and things like that. So why is it lower in energy to fill in 4s electrons if the energy of the 4s orbital is higher than the 3d orbital? And the reason for that, I mean, we can kind of see this here. So what we're looking at is a 3s orbital and a 3d orbital, not the 4s. We can look at the 4s as well. But note that the 3s orbital is larger than the 3d orbital. It's more spread out. We can be here, we can be here, and we have a more spread out orbital. The same is true for the 4s orbital. So the 4s orbital is more spread out than the 3d orbital. The orbital is actually larger. And so what that means is that to put electrons in a larger 4s orbital is lower in energy because those two electrons are now have more space to move about and have less electron correlation. They're less interfering with each other. So it's lower in energy to put electrons in this 4s orbital that's larger before you go to the 3d orbital that is technically lower in energy. That means you're cramming electrons together in a tight space. And for this reason, there's actually a much more complicated pattern of filling orbitals. And maybe you're aware of some of this. We have talked about some of this, but it's not as simple as you maybe learned in Gen Chem, where you look at the column and say, all right, these guys here, this is 4s2, 3d3, and that's true for everything. We can see if you look down here that we don't have 5s2, 3d3, we have 5s1, 4d4. And there are various exceptions to the general orbital filling rules that we discuss in Gen Chem. And these come from complex considerations for electrons. So for example, it's more favorable to have exactly half-filled or exactly filled d orbitals. So if we, rather than having a 4s2, 3d4 configuration, we always see a 4s1, 3d5 configuration. And the same here with silver, copper, and gold, the precious metals. They have a s1d10 configuration rather than an s2d9 configuration, and so forth. I don't want you to memorize any of these, but just be aware that the way we fill electron orbitals is more complicated. Finally here, we can use the electron orbitals to explain periodic trends. So we've learned some of these in Gen Chem, and we'll just briefly go through them here. But the atomic radius gets smaller as we go across the periodic table, and then gets larger as we jump down to the next row. And we can see that here based on the energy of the orbitals. We can explain this because the effective nuclear charge gets larger and larger and larger for these orbitals. The orbitals hold tighter and tighter, and so we get lower, we get smaller as we go along. And then once we get up to sodium, the effective nuclear charge is so large that we can't hold on to the electrons as tight, and the atom gets bigger. And then it goes, and we have this pattern. Another thing we can look at is electronegativity. Of course, this is going to go right along with effective nuclear charge. The higher the effective nuclear charge is, the higher the electronegativity. And we see this same sort of pattern here. And we can also use ionization energy. Again, the greater the effective nuclear charge, the harder it's going to be to ionize. Now, we do see a little bit of interesting patterns here. And these guys would correspond to here. So this would be boron, and this would be oxygen. And as we remove these electrons, we get to a perfectly empty p orbital and a perfectly half-filled p orbital, which is slightly more favorable than not. And so we see actually a dip in the ionization energy. It breaks the trend a little bit. But we can explain these periodic trends that we have physically observed by using our quantum mechanical models here. All right, so I'm going to conclude here this chapter by reviewing what we talked about this class and last class. Our Schrödinger equation is unsolvable for multi-electron atoms. So what we do to solve this is we make some simplifications and use computers to estimate the closest orbital energies that we can. We'll talk later about how computers use more complex models to make less assumptions in the future. We determined that electrons have to have a unique set of quantum numbers, and that includes the electron spin. So electrons can be spin up or spin down, which means that every orbital has room for 2 electrons. Our Pauli exclusion principle tells us that wave functions must be anti-symmetric, and we use Slater determinants to determine the wave function. And then finally, we were able to calculate orbitals that are in reasonable agreement with experimental data, both in terms of things like ionization energy, and then also things like periodic trends are in good agreement with these. So next time we're going to look into what happens now we have these electrons in their different orbitals, what happens when we excite them, what sort of transitions are possible, and what spectroscopy can we do with atoms.